The humidity hung thick over Atsugi airfield, 30 miles southwest of Tokyo, on a sweltering morning in late July 1944. Lieutenant Commander Minoru Genda stood before what remained of a Grumman F6F Hellcat, its battered fuselage bearing the scars of the dogfight that had brought it down 3 weeks earlier over Iwo Jima. But it wasn't the damage that held his attention. It was the 6 dark muzzles protruding from the wings, 3 per side, each one a Browning M250 caliber machine gun. Genda had flown combat missions since 1937. He had helped plan the attack on Pearl Harbor. He had survived Midway. He knew American fighters intimately, had studied their tactics, understood their capabilities. But standing here, running his hand along the wing leading edge where these weapons were housed, he felt something he rarely experienced. A cold understanding of just how fundamentally outgunned Japanese pilots had become. The recovery team had pulled this Hellcat from the sea after a Marine pilot, hit by anti-aircraft fire, had managed a controlled water landing near a Japanese-held island. The pilot was gone, rescued by an American submarine before Japanese patrol boats could reach him. But the aircraft, damaged yet largely intact, had been towed to shore and shipped to the mainland. Now it sat in a hangar at Atsugi, where Japan's best aeronautical minds had gathered to understand the weapon that was systematically destroying Japanese naval aviation. What they were about to discover would force them to confront an uncomfortable truth. American fighters weren't just better protected or more powerful. They were armed with weapons that turned every engagement into a catastrophically one-sided exchange. The 650 caliber Brownings in this Hellcat's wings represented a firepower philosophy so different from Japanese design, thinking that it challenged every assumption about what made an effective fighter aircraft. By July 1944, the kill ratio spoke for itself. For every Hellcat lost in combat, American pilots were destroying an average of 19 Japanese aircraft. Tactics played a role. Pilot training mattered. But increasingly, Japanese squadron leaders were filing reports that described a simpler, more brutal reality. Hellcats didn't need to outmaneuver Zeros, they just needed to get within range and fire. A single burst from those 650s was enough to obliterate aircraft that had been designed with every gram of excess weight stripped away. Genda watched as ordnance specialists carefully removed one of the Brownings from its wing mounting. The weapon was massive, nearly 5 feet long, weighing over 80 pounds with its ammunition feed system. The barrel was almost 4 feet of precisely rifled steel, designed to hurl half-inch diameter projectiles at velocities exceeding 2,800 feet per second. Even unloaded, the gun had a brutal, mechanical presence that Japanese weapons seemed to lack. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The team laid the Browning on a workbench, and the examination began in earnest. This wasn't the first captured American machine gun Japanese ordnance experts had analyzed. Browning .50 calibers had been showing up in intelligence reports since the beginning of the Pacific War, but examining one thing and understanding its battlefield effect was something else entirely. The Hellcat's installation gave them both. Here was the weapon system complete, 6 guns with full ammunition supplies, feed mechanisms, charging systems, and most critically, the remaining ammunition that would tell them exactly what American pilots were firing at Japanese aircraft. Chief Warrant Officer Saburo Taoka, who had spent 15 years in naval ordnance before the war, supervised the detailed disassembly. He had examined weapons from a dozen nations: German, British, Russian, Chinese. He knew firearms engineering as well as anyone in Japan. As the Browning's receiver came apart under his practiced hands, he kept pausing, looking more closely, examining tolerances that seemed impossibly tight for a weapon intended for mass production. The Browning M2 had been designed in 1918 by John Moses. Browning, refined through the 1920s and 30s, and by 1944 represented one of the most successful machine gun designs ever fielded. The basic operating principle was recoil operation. When fired, the barrel and bolt recoiled together for a short distance, locked together by the bolt's rotating lugs. Then the barrel stopped while the bolt continued rearward, extracting and ejecting the spent case, compressing the recoil spring, and feeding a new round from the ammunition belt. The timing of this cycle determined the weapon's rate of fire, approximately 800 rounds per minute for the AN-M2 aircraft variant. That meant each of the Hellcat's 6 guns fired roughly 13 rounds per second. Together, the 6-gun battery delivered nearly 80 rounds per second whenever the pilot pressed his trigger. In a typical 2-second burst, 480 half-inch projectiles would tear through the air toward the target. Tauka examined the bolt face, noting the precise machining of the locking lugs. The barrel extension showed minimal wear despite obvious combat use. The feed mechanism, which had to reliably grab rimless cartridges from a moving belt and chamber them at high cyclic rates, was a masterwork of mechanical engineering. Every component showed evidence of sophisticated manufacturing processes, precision machining, heat treatment, surface finishing that maximized reliability while minimizing friction. But it was the barrel that truly revealed the weapon's quality. The interior bore was chromed, a process that added expense and manufacturing complexity, but dramatically increased barrel life and maintained accuracy over thousands of rounds. Japanese aircraft machine guns typically used non-chromed barrels that wore rapidly, especially when firing the high-velocity rounds needed for air combat. Barrel replacement was a constant maintenance issue. The Americans had solved that problem by building better barrels that cost more initially but lasted far longer in service. The Hellcat carried approximately 2,400 rounds of 50 caliber ammunition, 400 rounds per gun. The recovery team had found roughly 1,800 rounds remaining in the aircraft's ammunition boxes, meaning the Marine pilot had fired approximately 600 rounds before being forced down. The ordnance specialists carefully examined these rounds, documenting every type they found. American ammunition loading for fighter aircraft followed a specific pattern designed to maximize effectiveness against different target types. The standard load mixed armor-piercing incendiary rounds, designated API, with tracer rounds, and occasional ball rounds for raw kinetic penetration. The ratio varied by unit and mission, but typically ran roughly 4 armor-piercing incendiary rounds to every 1 tracer. Tauka selected an armor-piercing incendiary round from the ammunition box and placed it on the examination table. The cartridge was enormous compared to Japanese aircraft ammunition. The brass case was nearly 5.5 inches long. The projectile itself was over 2 inches long, giving the complete round a total length approaching 6 inches. The loaded cartridge weighed approximately 4 ounces. The projectile design revealed sophisticated ballistic engineering. The bullet consisted of a hardened steel core, designed to penetrate armor, surrounded by an incendiary compound that would ignite on impact, all enclosed in a gilding metal jacket that engaged the barrel's rifling to impart stabilizing spin. The incendiary compound was typically a mixture of magnesium powder and barium nitrate that would ignite from the heat and shock of impact, starting fires in fuel tanks, oil systems, and wooden or fabric components. The tracer rounds used similar construction but added a pyrotechnic compound in the base that burned brightly during flight, allowing pilots to observe where their bullets were going. This visual feedback was invaluable for aerial gunnery, effectively turning every 5th round into an aiming reference. Japanese pilots had nothing comparable. Their rifle-caliber tracer ammunition was far less visible, and their 20mm cannon tracer rounds, while bright, had significantly different ballistic trajectories than their armor-piercing rounds, making them less reliable for aiming purposes. Tauka calculated the muzzle energy of the 50 caliber API round. With a projectile weight of approximately 700 grains, roughly 45 grams, and a muzzle velocity of 2,800 feet per second, each round left the barrel with approximately 12,000 foot-pounds of kinetic energy. For comparison, a Japanese Type 99 20mm cannon round, the primary armament of the Zero fighter, delivered roughly 9,000 foot-pounds of muzzle energy. The American 50 caliber, despite being a smaller caliber, actually delivered more energy per projectile than Japanese cannon rounds. The implications were staggering. The Hellcat's 6 guns, firing together, delivered 72,000 foot-pounds of kinetic energy per second of firing. The Zero's two 20mm cannons and two 7.7mm machine guns, firing together, delivered roughly 30,000 foot-pounds per second. The American fighter had more than double the destructive power, and that calculation didn't account for the reliability issues that plagued Japanese cannons or the limited ammunition capacity that forced Zero pilots to conserve shots. The examination moved to ballistic testing. The technical team needed to understand exactly what these 50 caliber rounds would do when they hit Japanese aircraft structures. They set up test panels representative of actual aircraft components, aluminum skin sections of various thicknesses, structural members, engine components, fuel tank samples. They would fire captured 50 caliber rounds and document the results. The firing tests took place at an ordnance range outside Tokyo. Japanese ordnance officers had test-fired captured American weapons before, but never with such systematic documentation of effects on representative targets. They mounted one of the Hellcat's Brownings on a fixed test stand and carefully loaded a belt of mixed ammunition identical to the combat load they had found in the aircraft. The first test target was a section of aluminum skin, 0.04 inches thick, representative of standard Japanese aircraft fuselage construction. The technical team placed it at 100 yards, a typical firing range in a deflection shot during a dogfight. The Browning fired a 5-round burst. The aluminum panel didn't just perforate, it effectively disintegrated. The armor-piercing cores punched through the thin metal as if it weren't there. Then the incendiary compounds ignited, creating bright flashes and starting small fires around each impact point. They examined the damage closely. Each round had created an entry hole approximately 3/4 of an inch in diameter, far larger than the bullet's actual diameter due to the aluminum's violent failure under high-velocity impact. The exit holes were even larger, raggedly torn openings where the metal had failed catastrophically. Surrounding each hole, the aluminum showed stress cracking and deformation extending several inches in all directions. A single 5-round burst had effectively destroyed a panel section, roughly 2 feet square. The next test used thicker aluminum, 0.08 inches, representative of more structural areas or doubler plates. Same range, same 5-round burst. The results were only marginally better. The armor-piercing cores still penetrated completely, though the holes were slightly cleaner. The incendiary effect was unchanged. Fires started at every impact point. Tauka watched these tests with growing dismay. Japanese aircraft used aluminum skin thicknesses ranging from 0.02 inches for non-structural fairings to 0.1 inches for highly stressed areas. None of it provided meaningful resistance to 50 caliber API rounds. The aircraft his pilots flew might as well have been covered in paper for all the protection the aluminum offered. They moved to structural testing. A wing spar section, carefully salvaged from a damaged Zero, was mounted in the test fixture. The spar was a masterpiece of lightweight design, an extruded aluminum alloy component that provided incredible strength-to-weight ratio through sophisticated cross-sectional shaping. It was exactly the kind of component Japanese engineers excelled at producing. The Browning fired another burst. 3 rounds hit the spar directly. The first round punched completely through, leaving a clean hole. The second round hit 2 inches from the first impact and encountered a slightly thicker section. It penetrated but fragmented, leaving the spar with a jagged wound and visible cracks propagating from the impact site. The third round hit adjacent to the second and completed what the previous impacts had started. The spar failed catastrophically, breaking in two with a sharp crack. 3 rounds, fired in less than half a second, had destroyed a component that represented hours of engineering design and precision manufacturing. The test team stood in silence, contemplating what they had just witnessed. In combat, a Hellcat fired not 3 rounds but dozens in a typical burst. The test had been conducted at 100 yards. Combat. Engagements often occurred at half that range, where striking velocity would be even higher. The ordnance specialists conducted additional tests against various components: a section of engine cylinder head, an oil cooler, a control cable assembly, a fuel tank section. The results varied in detail but told the same essential story. The 50 caliber API round defeated every component of Japanese aircraft structure with ease. The incendiary effect meant that even non-fatal hits could start fires that would doom an aircraft. The test against fuel tanks was particularly sobering. Japanese fighters used unprotected aluminum fuel tanks, a weight-saving measure that had been fundamental to achieving the long range and maneuverability that characterized Japanese designs. The test team mounted a tank filled with water, a safe substitute for gasoline, and backed it with aluminum plating to simulate the aircraft structure behind the tank. A 3-round burst from 100 yards perforated the tank in 3 places. Water sprayed from the holes under the internal pressure. The team drained the tank and examined it closely. Each projectile had punched through both the forward and aft walls, creating 2 holes per impact. The armor-piercing cores had continued through and struck the aluminum backing plate, penetrating it as well. They repeated the test with gasoline, observing from a safe distance through protected viewing ports. The result was immediate and catastrophic. The first round perforated the tank, and its incendiary compound ignited the gasoline vapor inside. The tank exploded in a fireball that consumed the entire test fixture. The aviation gasoline burned with intense heat, creating temperatures that would melt aluminum structures and ignite anything flammable nearby. This was the fate that awaited any Japanese pilot whose aircraft took fire into a fuel tank. Not a leak, not gradual fuel loss, but immediate catastrophic fire. American pilots had been reporting for months that Zeros burst into flames from minimal hits. Now the technical team understood why. The combination of unprotected fuel tanks and incendiary ammunition created a situation where a single bullet could destroy an entire aircraft. For comparison, they tested American self-sealing tank technology. The captured Hellcat's fuel tanks had been damaged during combat and recovery, but enough material remained for ballistic testing. They mounted a section of self-sealing tank and fired the same 3-round burst from the same range. The projectiles penetrated the outer skin and the rubber sealing layers, but the self-sealing mechanism functioned as designed. The synthetic rubber layers swelled in contact with gasoline, closing around the puncture within seconds. While some fuel leaked initially, the flow stopped quickly. A fire started at one impact point where the incendiary compound ignited, escaping fuel vapor, but it extinguished itself once the leak sealed and the vapor dissipated. The contrast was stark. An American pilot whose fuel tanks took hits would likely make it back to his carrier, the self-sealing technology buying him time and preventing catastrophic fire. A Japanese pilot with hits in his fuel tanks was almost certainly dead, whether from immediate explosion or from fire that would consume his aircraft in less than a minute. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The armament team expanded their testing to examine hit patterns and probability. In air combat, most firing occurred while maneuvering, with deflection angles and range constantly changing. Pilots didn't carefully aim single shots. They fired bursts while pulling G-forces, in turns, during climbs and dives. The question became, how many rounds from a typical Hellcat burst would actually hit a maneuvering target, and what would those hits accomplish? American gunnery training emphasized the concept of the cone of fire. When multiple guns fired together, their bullets spread in a cone pattern due to small variations in bullet trajectory, vibration, and the movement of the firing aircraft. The Hellcat's 650 caliber guns, mounted in the wings with roughly 3-foot spacing between the inboard and outboard guns, created a cone pattern that started relatively tight near the aircraft, but spread significantly at longer ranges. At 100 yards, the optimal firing range for a deflection shot, the 6-gun pattern would spread to approximately 6 feet in diameter. At 200 yards, the pattern spread to over 12 feet. This meant that aiming at center fuselage would result in hits distributed across the target aircraft's entire width. Some rounds would strike wings, some the fuselage, some control surfaces. The distribution was actually beneficial because it increased the probability of hitting something critical. The test team calculated. hit probability based on typical combat scenarios. A 2-second burst from all 6 guns meant 480 rounds fired. If the pilot achieved even 10% hit rate, a modest figure for a deflection shot at 100 yards, 48 half-inch projectiles would strike the target. If the hit rate reached 20%, which skilled pilots regularly achieved, 96 rounds would impact. They created a full-scale Zero mock-up using damaged aircraft components and placed it at the test range. An experienced anti-aircraft gunner, trained in leading moving targets, would fire the Hellcat's guns in realistic bursts, while the mock-up was towed past on a rail system to simulate relative motion. The test would reveal actual hit patterns under semi-realistic conditions. The first pass used a 2-second burst at 100 yards, with the target moving at roughly the relative closure rate of a deflection shot. The gunner aimed at the wing root, attempting to hit the fuselage, center section. When the mock-up stopped, the damage assessment team counted impacts. 63 hits had landed on the target airframe. That was 13% of the rounds fired, a realistic hit rate. But the distribution of those 63 hits told the real story. 17 hits had struck the engine, cowling, and firewall area. 21 hits were scattered across the wings, with several directly in the wing root where fuel tanks were located. 12 hits had impacted the fuselage. 8 hits had struck the tail section. 5 hits had damaged the cockpit area. Every major component of the aircraft had been hit multiple times. The engine would have been destroyed or severely damaged. At least 4 hits had penetrated areas where fuel tanks were located. The incendiary rounds would have ignited fires in multiple locations simultaneously. 2 hits had come close enough to the cockpit that the pilot would likely have been wounded or killed by fragments and secondary debris. The mock-up was a wreck. In combat, this aircraft would have been categorized as destroyed. The pilot, if he had survived the initial burst, would have faced an aircraft too damaged to control, with fires spreading through multiple compartments. His chances of survival would have been essentially zero. And this was from a single 2-second burst at modest hit rates. They repeated the test several times with different aim points and ranges. The results varied in detail, but remained consistent in outcome. The 650 caliber battery delivered overwhelming destructive power. Japanese aircraft simply could not survive being hit by a typical Hellcat burst. The lightweight construction that gave Japanese fighters their maneuverability and range became a fatal vulnerability when exposed to this kind of firepower. Lieutenant Commander Genda reviewed the test results with the technical team over several days. The data painted a picture he found difficult to accept, not because it was wrong, but because it was so devastatingly clear. The armament analysis explained combat reports that had seemed exaggerated or impossible. Pilots describing Zeros exploding from brief encounters. Formations being destroyed in seconds. Experienced aviators dying before they could react. The Zero carried 2 Type 99 20mm cannons, with 60 rounds per gun, and 2 Type 97 7.7mm machine guns, with 600 rounds per gun. The 20mm cannons were effective when they hit, but they fired slowly, around 500 rounds per minute, and the limited ammunition meant pilots had perhaps 7 seconds of cannon fire before running empty. The 7.7mm guns were essentially useless against American fighters with their armor and robust construction. Japanese pilots had developed tactics to compensate. They would close to point-blank range to ensure hits with the limited cannon ammunition. They would aim carefully, making every shot count. They would maneuver to get behind American fighters where armor was less effective. These tactics had worked in 1941 and 42 against earlier American fighters. Against the Hellcat, these tactics were suicidal. The American fighter's speed advantage meant it could control engagement range. If a Zero tried to close for a point-blank cannon shot, the Hellcat pilot could simply extend away using superior speed. If the Zero did manage to get within range, the robust American construction meant that even solid cannon hits didn't guarantee kills. Hellcats regularly returned to carriers with damage that would have destroyed Japanese aircraft. Meanwhile, the Hellcat didn't need perfect positioning or point-blank range. The 650s gave American pilots a weapon that could kill reliably at any angle and at ranges up to 300 yards. The high rate of fire meant they didn't need to be as precise as Japanese pilots. They could fire longer bursts, walk their fire onto target, and overwhelm Japanese aircraft with sheer volume of hits. Genda had the ordnance team calculate ammunition sustainability. The Hellcat carried 2,400 rounds total, 400 per gun. At the AN-M2's 800 rounds per minute cyclic rate, each gun would empty in 30 seconds of continuous firing. In practice, pilots fired in bursts, typically 1 to 3 seconds duration. A 2-second burst consumed roughly 27 rounds per gun, 162 rounds total from all 6 guns. This meant a Hellcat pilot had approximately 15 2-second bursts before running out of ammunition. In typical combat, pilots might fire 5 to 7 bursts during an engagement. This left substantial reserve ammunition for multiple engagements. Hellcat pilots could afford to take shots at longer ranges, could fire warning bursts to break up formations, could spray areas where they suspected enemy fighters were maneuvering. The Zero pilot, by contrast, had 60 rounds of 20mm ammunition total. At 500 rounds per minute, each cannon would empty in 7 seconds. A typical 1-second burst consumed roughly 8 rounds per cannon, 16 rounds total. The Zero pilot had perhaps 4 good cannon bursts before running empty. After that, he was left with the nearly ineffective 7.7mm guns. This asymmetry forced Japanese pilots into impossible choices: fire early and risk wasting precious ammunition on low-probability shots. Wait for perfect opportunities and risk never getting them against faster American fighters. Extend engagements to create more firing opportunities and burn fuel that might be needed to reach base. The tactical calculus favored American pilots at every decision point. The technical team prepared a comprehensive report for the combined fleet aviation staff. The analysis ran to over 300 pages, but the executive summary was brutal in its clarity. The Hellcat's 650 caliber armament represented a qualitative and quantitative firepower advantage that Japanese fighters could not counter with available technology. The combination of hitting power, ammunition capacity, and reliability gave American pilots an overwhelming edge in any engagement. The report included specific recommendations, though even as they wrote them, the technical team knew implementation would be problematic. Japanese fighters needed heavier armament, preferably 4 20mm cannons with increased ammunition capacity. They needed self-sealing fuel tanks to prevent catastrophic fires. They needed armor protection for pilots and critical systems. They needed more powerful engines to carry the added weight these modifications would require. Every recommendation ran directly counter to the design philosophy that had created the Zero and influenced every Japanese fighter since. That philosophy, emphasizing lightweight and maneuverability above all else, had worked brilliantly in the war's early stages. But the Pacific War had evolved into an attritional struggle where pilot survival and sustained firepower mattered more than aerial agility. Senior aviation officers who read the Hellcat armament report reacted with varying degrees of acceptance. Some acknowledged the findings and pushed for immediate design changes in upcoming fighter projects. Others questioned whether the tests accurately reflected combat conditions, whether American ammunition quality was really that consistent, whether Japanese tactics couldn't adapt to neutralize the firepower advantage. Captain Toshiki Tanaka, an experienced fighter squadron commander with combat service dating back to China in the late 1930s, provided perhaps the most insightful commentary. He had read both the armament analysis and the compilation of recent combat reports from units engaging Hellcats. His assessment was forwarded to multiple commands and became widely discussed among Japanese aviation leadership. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. Tanaka's report was blunt. "We have built fighters for a war we are no longer fighting," he wrote. In 1941 and 1942, our emphasis on maneuverability and range allowed us to dominate skies from Burma to the Solomons. Our pilots were superior in training and experience. Our aircraft could outmaneuver anything the Allies fielded. Victory seemed assured if we could simply reach the battlefield with sufficient numbers. But the Americans have fundamentally changed the nature of air combat in the Pacific. They are not attempting to outmaneuver us. They are not engaging in the traditional dogfights where superior agility wins battles. Instead, they have built fighters that negate our advantages while exploiting our weaknesses. The Hellcat's 650 caliber machine guns mean that American pilots do not need perfect positioning or point-blank range. They can kill us from any angle at distances where our lighter weapons are ineffective. More critically, Tanaka continued, they have built aircraft that bring their pilots home alive. When we shoot down a Hellcat, which happens rarely enough, the American pilot often survives. Their aircraft can absorb tremendous damage. Their armor protects them from our weapons. Their self-sealing tanks prevent the catastrophic fires that kill our pilots. They parachute into the ocean where rescue submarines retrieve them. Within days, these same pilots return to combat, more experienced and more dangerous. When the Americans shoot down a Zero, which they do with appalling regularity, our pilot dies. Our aircraft cannot survive the destructive power of 650 caliber guns firing incendiary ammunition. Our unprotected fuel tanks explode. Our lack of armor means a single bullet can kill. Our pilots have no second chances. Each loss represents years of training destroyed in seconds of combat. The mathematics of attrition haunted Tanaka's analysis. Japan had begun the Pacific War with approximately 3,500 trained naval aviators. By mid-1944, fewer than 1,000 remained alive. Training new pilots to replace losses had become increasingly difficult as fuel shortages reduced training hours and experienced instructors died in combat. American pilot training, by contrast, had expanded dramatically. The United States graduated over 20,000 naval aviators in 1943 alone. These pilots received extensive training, typically over 300 hours of flight time before seeing combat. They trained on aircraft identical to what they would fly in battle. They practiced against dissimilar aircraft to learn enemy capabilities and tactics. By July 1944, the average American Navy fighter pilot, arriving in the Pacific, had more flight hours than the average Japanese pilot he would face in combat. This represented a complete reversal from 1941, when Japanese pilots had averaged over 700 hours of training compared to roughly 200 hours for American pilots. The captured Hellcat's 650 caliber guns symbolized this transformation. The weapons themselves weren't revolutionary. The Browning design dated to World War I, but the Americans had understood that reliable, hard-hitting weapons installed in sufficient numbers and supported by adequate ammunition supplies would devastate aircraft built without protection. Japanese designers had known about armor and self-sealing tanks since the late 1930s. They had made conscious decisions to omit these features, believing that the weight penalties outweighed the benefits. Those decisions had been rational given Japanese strategic assumptions about a short, decisive war where pilot quality would overcome material disadvantages. But the war wasn't short, and material advantages compounded over time. Every engagement where Japanese pilots died while American pilots survived shifted the experience balance further toward the United States. Every Zero lost to a Hellcat's guns represented industrial capacity Japan couldn't replace, while American production accelerated. The ordnance specialists at Atsugi continued their examination of the Hellcat's armament system for weeks after the initial ballistic tests. They studied the gun synchronization system that ensured all 6 weapons fired simultaneously when the pilot pressed the trigger. They analyzed the ammunition feed mechanisms that had to reliably deliver rounds from boxes holding 400 cartridges each. They examined the harmonization, the precise alignment of the guns so their fire converged at the optimal range. Every aspect revealed sophisticated engineering and manufacturing quality. The gun mounts absorbed recoil forces that would have torn lighter structures apart. The electrical firing circuits included redundancy so that individual gun failures wouldn't prevent the others from operating. The ammunition boxes were designed for rapid reloading by carrier deck crews, with clear markings and foolproof installation to prevent mistakes during the chaos of flight operations. These weren't just weapons. They were components of an integrated system designed for sustained combat operations under the brutal conditions of carrier warfare. Japanese aircraft weapons, while often ingenious in design, suffered from reliability issues and maintenance complexity that reduced their effectiveness in prolonged campaigns. The Type 99 20mm cannon that armed most Japanese fighters was a capable weapon when properly maintained, but it was sensitive to temperature variations, required frequent cleaning, and had a tendency to jam if ammunition wasn't stored correctly. In the humid, salty environment of carrier operations, these issues multiplied. Pilots would often find that one or both cannons malfunctioned during combat, leaving them with only the nearly useless rifle-caliber machine guns. The Browning 50 caliber, by contrast, was renowned for reliability. The chromed barrel resisted corrosion. The simple, robust design tolerated dirt and environmental stress. Carrier deck crews could maintain the guns with basic tools and minimal specialized training. When a Hellcat pilot pressed his trigger, all 6 guns fired. That reliability was as important as the raw hitting power. By August 1944, as American forces fought their way across the Pacific, the Hellcat's dominance had become absolute. Japanese pilots referred to encounters with the American fighters as certain death missions. The psychological impact was devastating. Knowing that enemy aircraft carried overwhelming firepower, while your own weapons were marginal, at best destroyed morale faster than actual combat losses. Lieutenant Saburo Sakai, who had examined the captured Hellcat personally, later wrote that understanding the technical superiority of American armament was more demoralizing than losing battles. We could accept defeat if we believed better tactics or greater courage might prevail, he recorded in his private journal. But seeing the 650 caliber guns, understanding their destructive power, knowing our aircraft offered no protection against them, this removed hope. We were not fighting a war we might win. We were flying to our deaths in aircraft that could not protect us against weapons we could not match. The broader implications extended beyond individual aircraft armament. The Hellcat's guns represented American industrial philosophy. Build reliable, powerful weapons in massive quantities, install them in robust platforms, train pilots to use them effectively, and support the entire system with logistics that ensured ammunition, spare parts, and maintenance were always available. Japan's industrial capacity couldn't replicate this approach. Even if Japanese designers had wanted to copy the 6-gun armament layout, manufacturing Browning-equivalent weapons at scale was beyond Japanese capacity. The precision machining, the specialized steels, the chrome plating, all required industrial infrastructure and expertise Japan lacked. Some Japanese designers proposed mounting captured American 50 caliber guns on Japanese fighters. The idea was rejected, not for lack of will, but for practical impossibility. The weapons required different mounting systems, different ammunition feeds, different electrical systems. Adapting a Japanese fighter to use American guns would require complete redesign. And even if that were accomplished, where would ammunition come from? Japan couldn't manufacture 50 caliber ammunition to American specifications. The technical team's final report on the Hellcat's armament concluded with a section that became infamous among Japanese aviation circles. It was titled simply "Irreconcilable Differences," and argued that the gap between American and Japanese fighter armament reflected irreconcilable differences in industrial capacity, strategic vision, and design philosophy. The Americans have built an air force designed for sustained attrition warfare, the report stated. Their fighters carry weapons that can destroy ours with ease. Their aircraft protect pilots so they survive to fight repeatedly. Their industrial system produces aircraft, weapons, ammunition, and trained pilots faster than we can destroy them. They are not trying to be more maneuverable or more elegant. They are trying to overwhelm us with firepower and pilot survivability, and they are succeeding. We have built an air force designed for short, decisive engagements where pilot skill and aircraft agility would prevail. This strategy worked brilliantly for 18 months. It is now failing catastrophically because the war is not short, and our qualitative advantages have been overcome by American quantitative superiority and better pilot protection. The report recommended immediate development of heavily armed, protected fighters, even if it meant sacrificing the maneuverability that had defined Japanese aviation. But by August 1944, such recommendations were academic. Japan's aviation industry was already staggering under bombing raids, material shortages, and loss of experienced workers. New fighter designs existed on drawing boards but would arrive too late in too few numbers to matter. The captured Hellcat remained at Atsugi through the war's final year, occasionally used for training purposes, so Japanese pilots could familiarize themselves with American aircraft they would face in combat. But mostly it sat in its hangar, a silent testimony to the gulf between Japanese and American aviation technology. When American occupation forces arrived at Atsugi in August 1945, they found the Hellcat where Japanese engineers had left it, still bearing Japanese markings and technical instrumentation. The detailed reports Japanese specialists had compiled were discovered in archives, 300 pages of meticulous analysis that revealed how thoroughly Japan's technical experts had understood their disadvantage. American intelligence officers reading these reports noted the professionalism and accuracy of the Japanese analysis. These were not defeated men making excuses. They were skilled engineers, honestly assessing enemy capabilities and clearly explaining why their own forces were outmatched. The Hellcat armament analysis, in particular, showed sophisticated understanding of the weapon system's effectiveness. The legacy of that captured Hellcat and its 650 caliber guns extended far beyond World War II. The Browning M250 caliber machine gun remained in American service for decades, eventually becoming one of the longest-serving weapons in military history. The basic design that had proven so devastating against Japanese fighters in 1944 was still arming American aircraft, vehicles, and infantry positions into the 21st century. For Japan, the lessons were absorbed into post-war aviation development. When Japan rebuilt its air forces after the war, the emphasis shifted dramatically toward robust construction, pilot protection, and reliable, hard-hitting armament. The philosophy that had created the Zero, brilliant in its way but fatally flawed for sustained combat, was abandoned in favor of approaches that prioritized survivability alongside performance. The story of Japanese officers examining that captured Hellcat and discovering the devastating effectiveness of its armament became a case study in how wars are won and lost at the intersection of design, philosophy, industrial capacity, and tactical evolution. The 650 caliber guns weren't magic weapons. They were simply the right tools, properly implemented, supported by an industrial system that could produce them in quantity and employ them effectively. Japanese pilots had fought bravely, often brilliantly, in aircraft that could not protect them against weapons they could not match. The tragedy was not lack of courage or skill, but strategic miscalculation about what kind of war they were fighting and what kind of aircraft would be needed to win it. By the time the captured Hellcat revealed these truths with brutal clarity, the opportunity to change course had long since passed. Lieutenant Commander Genda, who had stood before those 6 gun muzzles on that humid morning in July 1944, survived the war and later became a general in Japan's post-war air self-defense force. He never forgot the moment of recognition when he understood what those weapons meant, not just for individual engagements, but for the entire trajectory of the Pacific Air War. In his memoirs, he wrote simply, "We built beautiful aircraft for the war we wished to fight. The Americans built brutal aircraft for the war that actually existed. That difference decided everything."